Good morning, Professor Sahdev. So we welcome you in this program. And then before I will introduce a little bit about you, so participant and all of us can know a little bit about you, then we can start the session. So Professor Desdeep Sahdev is the founder director of Quazar Research and the CEO of Quazar Technologies, an innovative high-tech Delhi-based company working in the area of high-resolution microscopy, condensed matter physics, and nanotechnology. Prior to this, starting this company, Dr. Sahdev was a senior member of the physics department at IIT Kanpur. He taught there about 30 years, and in IIT Kanpur, he joined after several years of teaching and research in leading groups at Cornell University, University of Pennsylvania, and the International Center of Theoretical Physics, Italy, among others. While at these centers, he worked as and interacted with several Nobel laureates, including Professor Abdul Salam, Ken Wilson, Steven Weinberg, and Richard Feynman. Professor Sahdev has made outstanding contributions in several branches of theoretical, computational, and experimental physics. Focusing only on the latter, his group has developed an internationally competitive standards, a chemical vapor deposition system for preparing samples and micro devices, as also scanning probe microscopes and physical quantities measurement systems for characterizing them. His group has authored world-class uh, packages for scientific computation, including Bolt. So they especially has developed one program, Bolt, which is very popular, and this can solve Boltzmann and Boltzmann-like equations, which has several novel and interesting properties of graphene and other two-dimensional materials. So graphene and other two-dimensional materials have been understood with the help of the Bolt program. So this program is a very popular program. And then you have several other contributions as well. So we do not have much time. So Professor Sahdev, we welcome you for this program. And then we are just waiting for your this motivating and encouraging words. So this participant of this particular program, the forecasting and fostering demand. So they get this particular session of today, so they can get benefit. I hope this your experience is starting this company, being the professor for about 30 years and then moving to the company afterward. This will be very nice experience to share with the participant, this faculty members and among us. So we welcome you and thank you for accepting our request for the program. Thank you. We welcome you. Please.
Yeah, can you hear me?
Yes.
You can hear it clearly? Okay. I guess we can probably begin. 1 second. What is going on? Yeah. All right. So the audio is fine.
Yes. Everything is fine.
It's clear. Okay, fine.
Yeah, your camera.
All
Maybe
right.
you can focus a little. Miss. Yeah, you can adjust your camera. This.
Right. That's what I'm trying to do. Okay. Is it fine now?
No, sir. We can. Yes. Now it's fine. Very good. Yeah. Thank you, sir.
Okay. Can you see me now clearly?
Yes. Yes, sir.
Okay. All right. All right. So good morning, everyone. I will be. I'll simply be telling you about our attempts at trying to build up instrumentation and computation indigenously, and this is just a case study. We started long before the whole idea of AtmanirbharBharat, etc., started becoming uh, uh, right before it started becoming fashionable. And I will just tell you exactly what we did and what happened. And only towards the end will I come to making a few observations and probably trying to give you, which might turn out to be useful in your case. I'm not into the business of giving advice to people, which, uh, unless they are very closely working on something and all the questions that they asked are very pointed questions. But all I can do is I can share my experience. All right, the next one, next slide, please. All right, now strangely enough, this whole company started not with the idea of doing a business, or in fact even with the idea of making any money at all. It started because I had trained in the West, mostly a lot in the US, in some of their top universities. I was at Cornell, I was at UPenn, and while I was there, I was interacting with some of their best scientists and well, mostly scientists, because I was a physicist. And while I was there, I watched these people very closely to see what it is that they were doing, and trying to figure out why their science and technology was so far ahead of where we were. And after I came back to India, and by the way, after I came back, which was about 25, 30 years ago, my passport is expired. I mean, it expired 25 years ago. So, I mean, that shows you how important it was for me to be traveling abroad. I mean, the whole thing, every single thing that I'm going to be telling you about has all happened in India without any collaborations from outside. All right. In fact, we almost had, in fact, almost zero interaction with the West after that, except, of course, through the internet. Anyway, so the idea was that we had to now start building up a strong ecosystem for ourselves. I was, after all, a professor. And what I noticed was that a lot of the people that I was training were all, as soon as they graduated, they started running various embassies, begging for visas and so on. And that was very humiliating. I mean, all these people should have been working in the country, building up a very strong base for science and technology. So now the question that that came to mind was, what is it that we really need to do in order to make this, to build a proper ecosystem where things actually can happen. All right. So the first thing that we needed was experiment. And by the way, I was a theorist. I'd never even entered a lab, even done any engineering or anything like that. I had qualified, of course, with a good rank for the IITs. Once dream of joining the IITs. It was not something I was at all interested in doing. I did eventually, ironically, end up being a professor at IIT, but certainly not a student. Anyway, so because I was interested in physics and science, and the IITs didn't strike me as very attractive at that point, although they have improved considerably since. Anyway, so we needed to build up experiment. Next, next, but instrument, wait, please go back. So now if we had to set up experiments, we had to really get control of instrumentation. We had to be able to build instruments. Now, the building of instruments, of course, was going to require a lot of engineering and so on. And it was not something that I was particularly, I had any exposure to. It was zero. And then, of course, in modern science, computation and computational packages and scientific computation is an absolute must. So that is another thing that I really had to now come up. So these were the four things, but of all these four, the one that was furthest away from where I was instrumentation. So I decided that I would tackle the problem from the instrumentation. Next. All right, so now what was our approach going to be? Well, the whole idea was to do cutting edge research and to start becoming competitive in R&D. So the approach was that we would build high-tech instruments, enough of them to build a full laboratory, And that would allow us to start doing this. In a laboratory where every single instrument had been built by us, it would be modified by us, and so on. All right. So how would we actually make this happen? Well, the idea was, all right, next, we would develop these instruments, turn them into marketable products. Next, figure out every possible thing that we could do with these products. So these would be, we would work out all sorts of applications. That would generate the finance for this entire thing. And that finance now, through marketing, and that finance would allow us to, would finance the next set of instruments. And we would keep going through this loop over and over again. Once again, turning the instruments into marketable products, then working out the creative application for this, till eventually we got to a point where we had a whole laboratory, and then we would be able to do research, which was finally which was actually the aim. So we were just going to use entrepreneurship and self-reliance, etc. Was simply research and cutting edge research. We some of it would be, of course, inevitably the industrial industry-based research, but a lot of it, I mean, I was interested in cosmology, in the origin of the early universe, in astrophysics, and so on. So some of the instruments would eventually be instruments through which we can start probing other galaxies and so on. All right. So that was the whole idea. This was very, very far removed from the current concept that people have of having a company and just trying to make money. This was an attempt at trying to make science and technology. All right, so I had to give you that background, and I'll just give you now the journey towards making our first major instrument, and then very quickly we'll move on to to how we further implemented all of this. And of course, we have not taken any money from any venture capitalists, not taken any money from the government. Every single thing that we've done and everything that I'm going to tell you about has been done through our own understanding and knowledge of science and technology itself, and all the skills that we have built up. So in principle, every single thing that people have been now talking about, they've been talking about skill building, about Atmanirbharata, I mean, which is the theme of this particular seminar or webinar. Trying to become self-reliant. All of that was something that makes a lot of sense. It's very sensible stuff. It makes, in fact, so much sense that we were already deeply into the whole thing in 2002 when the company began. It was about 10 or 15 years before all of these things, as I said, became passion. Next. All right, so one of the instruments that we built was a scanning tunneling microscope. I do not expect you to know what it is because we ourselves didn't know what it was when we started building. We started, we pulled out papers, we started reading about it and so on. But let me quickly explain what it is. All right. Now, if you open out your computer, you will get a card, which is where everything is on the centimeter scale. If you take a small portion of that computer, you magnify it, of that card, and you magnify what you're seeing, you will see tracks of the sort in the second image. And now all these tracks and everything are on the millimeters. Next, there is an integrated circuit there. We open it out, you will see similar circuits, and they're all on the micrometer scale. Next, inside this integrated circuit, there are embedded integrated circuits. All right, which if you magnify, everything is going to be now on a 100 nanometer scale. You get a thing of this sort. The yellow line is gold. It's a streak of gold, and everything's been mounted on silicon. You magnify it further, and the first of these images of gold at 10 nanometer scale has been done with our own microscope. Silicon does not image very well in air, so we've taken that from the net. And now, if you go one step further, you actually start seeing atoms. All right. Now, so this was the instrument that we want to now make. Next. Now, it's very interesting how this instrument works. In order to understand that very quickly, think not of a person who has eyes, but think of yourself, in fact, when you're blindfolded and you're now trying to image a certain surface. So what you'll do is that you either, let's think of a person who's blind and he's trying to recognize a friend who's being mischievous and does not call out his or her name. Well, the blind person will touch the friend's face and will scan it, feeling the eyes, the nose, the eyebrows, and so on. And then as she or he is feeling, the blind person feeling each one of these features, the um, there are sensations at the tips of his or her fingers which pass through circuits in the arm and go all the way to the brain. And in the brain, there's an image processing program that converts these sensations into an image of the friend's face. Now, the scanning tunneling microscope works in exactly the same way. It involves scanning. So you have this tip, this gray looking thing. You have a probe, which is like the finger of the blind person. And then with this probe, you scan the surface. So the orange thing is the surface. And so you start scanning it, and you apply a small battery you connect between the probe and the surface. All right. Now, when you do that, a small current begins to flow. That current is in the range of nanoamperes to picoamperes. So it's 1 ampere times 10 to the minus 9 or 10 to the minus 12. It's a small thing. It's like the sensations at the tip of this probe, which is at like sensations at the tip of the fingers. And you take these currents that you have acquired and you pass them to a computer, which is like the brain of the blind person. And in the computer, you run an image processing program, which converts these tunneling currents, these quantum tunneling currents, into an image. All right. So that's where the name comes from. A scanning quantum tunneling current microscope. You have to scan, and what you acquire, the sensations that you acquire are quantum tunneling currents. And of course, this is the microscope. Now, this is what we had to make. And it was a major challenge. I mean, we had no clue of how we were going to measure currents down to a picoampere. And it's even worse. You see, the reason why this thing is so sensitive is that this current is flowing across a gap. Now, if this gap is reduced by just one atomic distance, the current will increases by a factor of 10. So it makes it very, very sensitive. And that's why, because even an atomic distance shift can be detected, and that is why you're able to see atoms. But there is a flip side to it. If somebody walks in the room and your probe just shakes by a small amount, what is a small amount? It shakes by just the size of an atom. Your current will start going up and down by a factor of 10, and you won't be able to image anything at all. So you have to keep the vibrations down. In fact, in our microscope, we have brought them down to something like 1/50th the size of the atom. So when we were beginning to make this, we said, God, yeah, how are we going to do all of this? Yeah, how are we going to make something that where the vibration is 1/50th the size of the atom, where the currents that you're picking up are in nanoamperes and picoamperes and so on. But I mean, we just decided that if we had to make it, we would just have to figure it out. All right, next. Next. Okay, so this is what the thing looked like, and this is all done in collaboration with now with Anjan Gupta, who's now a faculty member. He was then a student. No, not yet. No, please hold on. Right. And then with Ajit and Kundan Singh of the Inter-University Accelerator Center. So all of us were, I mean, these people were in Delhi, Anjan was in IIT Kanpur, and all of us were now collaborating. We didn't have the confidence that we could build the entire electronics at one go. So we built it in steps, and we put it inside boxes. And on the right-hand side, in the aluminum box that you see on top, the gray box, scan head. Below it, we had to now reduce the vibrations that were all involved. And those vibrations we tried reducing by putting using a stool and putting the feet of the stool in sand and so on, in the hope that when the vibrations come, the particles of sand will rub against each other and the energy of the vibration will be taken. Now, looking at this, you would never think that you could actually get atoms out of it. But, miracles never cease. And we would, by the way, we would put everything inside a basement and we would scan at night and all that stuff. So once we had stepped out for dinner and suddenly we got a phone call. And the person working on this said that I think you should come back. I said, oh God, now what is broken? There's nothing is broken. I think I've started seeing the atoms. And so we immediately rushed back. And now, next, this is what he showed us. Next. The whole thing, we are now zooming. Next. We zoom further. Next. 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 Now, suddenly, a small amount of image processing, and we start seeing the atom. I said, God, yeah, this thing has really worked. This is quite remarkable. And then, of course, we kept on scanning, and we at about midnight, we called up Kundan. He said that, look, I think we got the atoms. If you want to see them, you can come tomorrow. He says, they might not be there tomorrow. I'm coming right now. He jumped onto a scooter. He came over. We scanned it till about 1:45 at night. And then we suddenly remembered that the last student cafe in IIT Delhi, we were next to IIT Delhi. All this is happening in Delhi, by the way, not Kanpur. And we immediately rushed to have coffee by way of celebration. And Kundan took the first sip of coffee and he got up and he says, we Indians, we don't have self-confidence. And then I said, thank God it's coffee. If it's something else, I don't know what kind of speech would have come up. Anyway, next. Now, when I said that we made it, there is a difference between just assembling things and actually making them, understanding them right down to the basic levels. I mean, there are many layers that you can feel through. But what we had done was that we designed and machined every mechanical component with our own hands. Next. And then we designed and soldered every bit of the electronics ourselves. Next. And in fact, we've taken the electronics to 4 generations now and made it more and more powerful. We wrote every line of the software. Next. And now please stop at this point. So, and then we made the whole thing user-friendly. This came out of a master of design thesis at IIT Kanpur, which was guided by me and Amit Ray, who was heading the design department. And the student was Ameya. And now there was one other major innovation that was required in order to make this thing happen, and it had to do with language. All right, and you see, I will explain it briefly as follows. When Einstein developed his theory of relativity, he didn't speak a word of English. He developed it all in German. The first phase of electromagnetic theory was entirely in French. It was developed by Coulomb, whose full name was Charles-Auguste Coulomb. It was Bio, Sava, Ampere, 1 ampere of current, Ampere's law. All these guys were French and they were writing in French and everything happened in French. It was only with Faraday and Maxwell that it shifted to English. All of quantum mechanics developed in German. The whole theory of superfluidity developed. It was between Landau and Kapitsa. It developed in Russia. So the Germans were doing all their physics in German, the French in French, the Italians in Italian, the Russians in Russian, Chinese in Chinese, the Japanese in Japanese. But Indians seem to think that without English, you can't do any physics. And so one of the major innovations was that we switched, because we draw on people who are, I will be saying certain things later about the kind of educational system we have. But it is simply not up to the mark. And we do not have people who have the skills to build things of this sophistication at all. All of them are coming out of a different background from the ITIs, from polytechnics and so on. And all of them speak only Hindi, they don't speak English. So so now the big innovation was that we switched to Hindi, and that became the common language between everyone. And the entire technical documentation for building this whole instrument is in Hindi. Next. as you can see. I mean, all of it is in Hindi, and that was another major break. Next. Okay, so then this was what the thing looked like, and now this we converted this into a marketable product. Next, the entire electronics went into the white box that you see below the computer. You have and the entire scan head was inside this, and the whole vibration isolation stage. Everything went onto the thing on the left. And this was the first product that we ended up selling to NPL, the National Business Laboratory. Next. And now routinely we can make these at once a week. I mean, we make 5 or 6 SCMs in every 6 weeks. And every time we make them, we resolve the atoms and so on. All right. And that's how we know that the whole thing is working. Next. Okay, so now by now we have then installed 48 or 49 installed 48 and sent out 49 of these all told to the IITs, ISAs. SSPL is a DRDO lab. NPL, of course, is CSIR, IGCAR, TIFR are DAE labs, Department of Atomic Energy, many universities, and also to NTU Singapore. They found out about a microscope, they wrote to us, and then they put out the specs in an open tender on the government of Singapore website, and we easily won all of that, and we went and installed, and of course got the whole thing running. Next. Now this is more than all the MNCs operating in India combined, and while we have sold about 48, 49 of them, they probably sold 3 or something. Next. And why? Because we have better specs by now. For air STMs, we have better support, of course, at the level of instrumentation, application, expertise. As you can see, I mean, you have very good people who made this, and of course, a better price. Next. Okay, so now the whole point was, how do we close this whole loop? All right. Now, so we had just made one instrument, but we obviously had to build a lab. We now had to make something with which we could prepare samples. And then ये जितेंद्र को बुला, just a second. अच्छा जितेंद्र को बुलाकर ये call back करा. Yeah. So we had to think with which we could prepare samples, a sort of a mini fab with which we could make actually devices, etc. We of course had to be able to characterize them, so we had to build many more instruments. And then we next, we would of course, in order to understand all the results and everything, we would have to build models, simulations, computational packages, and so on. And then that would allow us to really start doing research at a competitive level. So we went on next. We then built, this is a chemical vapor deposition system that we built, with which we can now make all sorts of samples, and this is the graphical user interface. Once again, the same principle was used. Every mechanical component was designed, machined by us. The entire electronics, of course, was designed and soldered and protected by us. Every line of the software was written, the entire GUI, everything was done by us. And we started now making chemicals and making various types of thin films and graphene. And in fact, next, we made crystals of molybdenum disulfide. This is what the furnace looks like when you open it. It has 12 zones. We can completely profile the temperature and so on. And this is what the graphical user interface looks like. Next. Okay, then we built a system for studying the electrical and magnetic properties of samples. I mean, we're talking about DC resistivity. We can measure it over 20 orders of magnitude, from a micro, 10 microohms, or in fact, right down to a microohm under best of circumstances. and going up to 100 tera ohms, which is 10 to the 14 ohms. And under the best conditions, we can go up to a beta ohm, which is 10 to the 15 ohms. So we're talking about 20, 22 orders of magnitude. And this is with our own electronics. We are not using stuff that we are buying off the shelf from anyone. We designed all of these from scratch. Where we start, of course, is with the chips, with the integrated circuits and chips, and of course resistors, capacitors, etc. Those we are buying, and some of them we are importing. But the import component of everything of all our products is something like 5% of the final price. So 95% is the value add that's happening out. Then AC magnetic susceptibility, magneto resistance, all coefficients, these are all for magnetic properties with excellent temperature control. Next. There are a whole bunch of installations for this next. And this was with Ashok Rastogi of XTNU. Now this is what the thing looks like. All right. And this is it's a a cryogenic system, and it goes down to minus 200 degrees and with excellent control. Control is like 0.03 degrees Kelvin. Next. And these are some of the results. These are 19 curves that you've gotten from 80 Kelvin to 450 Kelvin. This is the third graph at the bottom is for a diode, and the red line is the experimental data. The blue line is the theoretical bit. Next, and then we built this a vibrating sample magnetometer, 2 pH curves and MH curves. All right. Next. And then we needed a diamond cutter to cut samples without damaging them and so on. These were themselves cost 4 or 5 lakhs when imported from outside. We managed to bring it in and cut the price down in half for about 2 lakhs. And it has all the specifications with 4 5 lakhs. Next. And so this is the lab that we finally built up. I mean, starting from the left, we have the first version of the chemical vapor deposition system. Now, as you can see, it has evolved a lot. The next one, the blue thing, is a gas chromatograph. The next thing after that is an STM that that's the diamond cutter. The next one is the STM, and then we made the scanning tunneling microscope that I described in some detail. Then we made an atomic force microscope, which we haven't brought into the market, but made it for ourselves. Then as you go around moving to the right, all right, from the back, you have a vacuum version of the STM. You can put the whole scanning tunneling microscope inside a vacuum and you can evacuate. The next thing after that is the physical quantities measurement system, and then you have the vibrating sample magnetometer. And apart from this, we started making. Now there was another student of mine. All of this, of course, to be able to do this, you have to have absolutely top level people working. So these are people who could have gone to the top universities in the US. They did not go and they stayed back. They worked. Then they managed to inspire one of the other people who had actually gone to the US. And after he finished his PhD, he had offers of postdoctoral offers, the top postdoctoral offers in the US, from Princeton, from Harvard, from Berkeley. And he was in public meeting, was asked, well, what will you be doing next? So which of these places will you take a job in? And he was able to tell them that I already have a job. He had promised to come back and work with me. And so he says, I already have a job. They said, where? He said, in India. He said, well, you're turning down Harvard, Princeton, Berkeley. He said, yeah. And he came back, and he came back 4 years ago. And these 4 years, he's developed the world's fastest package for solving the Boltzmann equation. which is something that we will eventually be trying to take to the market also. And hopefully the first three people who will buy it from us will be precisely uh, Harvard instrument. Next. Okay, so this was a very brief background, all right. Of and now please stop here. Just leave this line there, and now I will. This is the one slide that I've prepared, in which I'll be making. There will be a number of observations and insights into this whole process, and I'll be explaining some of the basic concepts. I think that I've now taken 31 minutes. I will go up to for another 14 minutes. I'll speak on the slide. That'll be 45 minutes exactly. And then we have 15 minutes of questions, and we'll close the session. Please, as far as I'm concerned. I mean, all of you can continue on to the next speaker. All right. Now, the first thing is that R&D driven companies are completely different from trading outputs. I mean, the concept that we so far have within this country, there are very, very few R&D driven companies, if any. The only concept that we have of a company is, I mean, there are every shop. I mean, there are lots and lots of shops in every single town in India. All right. And all these shops are mini businesses of, and all shop owners are entrepreneurs. So the first thing is that whenever people are talking about R&D driven companies, they seem to think that they're just shops. That there's just some sort of trading going on. Everyone just assumes that we're just buying some stuff, fitting it together, and then selling it. The whole idea that you could actually understand the physics, go 3 levels deeper, you could understand it in the same way in which uh, the innovators in the West and in other places that fully understood it, is a concept which is still alien. But this is exactly what we are doing. And we are not doing it. The assumption is that, well, without the white man, you won't be able to do it. Now, to some extent, that is true. We've also, of course, we didn't invent the scanning tunneling microscope. If we had invented it, we would get the Nobel Prize. We would have gotten the Nobel Prize. The Nobel Prize went to two Germans who invented it in Zurich, Switzerland. However, the microscope that we have built is every bit as good as the one that they had. That is being built by any of these companies. Even to get to that level, you have to understand it, and our understanding is at least the same as the understanding of the people who actually. I mean, we have done fairly deep analyses and developed this entire thing. So this whole thing is actually a science-based thing. It is not predominantly a Banya activity. It is coming from a completely different direction. All right, we are not shopkeepers. We haven't opened a pawn shop. Try to just make money. All right, next. All right, the next thing is, if you have to do a thing of this sort, you really need teamwork. And now teamwork is something that Indians are just absolutely zero. I mean, not only zero, they're -10. You bring in right now, we shudder at the idea of bringing in a new person into the company, because they'll come in with all the backwardness. I mean, it's the best way of first of all, you have to understand what teamwork is. Every guy puts down on his resume, I'm a team player, I'm this, that. All right, which is absurd. They don't know what they're talking about. Now, let me use the analogy of football to explain to you what teamwork is. A friend of mine had quite famously said, and this is a deep statement, he says football would be easy to play if one didn't have to score. If you didn't have to score a goal, anyone can kick the ball. Now, and of course, there is still some amount of practice. People like Pele and other good football players could keep the ball in play and not let it touch the ground for 10 minutes. They could just keep it, keep hitting it with their head, with their foot, with their knees, all according to the rules. So there is some amount of practice there. But by far the largest amount of practice is in coordinating. In order to score the goal, you have a very, very narrow margin for error. You have, if you kick the ball too hard, it's when you get close to the D that everything starts happening. You kick the ball, if you kick it a little too hard, it'll go over the goal line before your own player can get to it. You kick it too softly and he won't get to it, and the opponent will get to it. Just getting this right, all these Olympic teams and the ones participating in the World Cup are uh, what's it practicing 8, 10, 12 hours a day for 4 years in order to just get that right. That is the kind of teamwork that is required to do the kind of work that we are doing. You need all the people coming in every single day on time, and they are all talking to each other. They're all and there are people doing all sorts of different things. There are people working on electronics, working on mechanical stuff, working on physics, working on writing programs, working on scientific computation. You need people with just very different skills and all combining in a single team to score a goal. And that takes years and years of practice. It is something which is completely absent in our educational system. Even the biggest suspicion of teamwork is not there. And it is a total disaster because of that. Whenever people are thinking, they're passing out of college, they've known almost nothing. And they already want to start a company. The only company they'll start is basically a pawn shop. If they want to really build anything up further, figure out how you can have a team of 3 or 4 or 5 people working together. All right. And how different skills can be combined. Next. All right, marketing a scientific instruments is a fundamentally scientific activity. It's not a marketing activity, it's a scientific marketing is more scientific than marketing. You have to figure out what you can do with these instruments. And if every new innovation that you can come out with is a breakthrough in science. And that whole coupling between the instrument and the science is a very important thing. Now we need after having built the instrument, all right, we need to figure out all the applications. Now applications, I mean, once you have, for instance, chemical vapor deposition system, you have to be able to make molybdenum disulfide. You have to be able to make tantalum disulfide or tantalum diselenide, or make graphene, or make um, or make carbon nanotubes and so on. Now, knowing how to make all of these and making sure that with those instruments you can make these as well as people anywhere in the world can make them is again deeply scientific. But if you can do that, then of course you can show it to your clients, you can convince them, and that is the that itself is very good people in terms of science. And of course, that we have to distinguish marketing from sales. Sales is what you see most traders and Indians are at best traders. They're not, innovators or anything of that sort. They will just buy the thing from abroad, even when it's scientific stuff. So when you're buying all the computers that you bought have all been made outside the country. They've been invented outside the country. I mean, all the phones on which we are doing all of this are all imported. So there is no scientific part in that because there is no even the manufacturing. You just say what we are doing is we're asking these companies to come and manufacture in India. I mean, that's a step forward. It's a little better than just importing all the stuff. And because of that, over time, perhaps some amount of innovation may actually begin. But most of what is now referred to as marketing is just sales. All these you have this huge number of mobile shops all over the place. The product is already there. There's nothing before the product. I mean, it's just being imported and it's being delivered to them by also some of these foreign companies like that. So, DHL and so on. And all they're doing is they're just selling it. Now, selling itself requires a certain amount of gimmickry and in this country, you have to run into a very entrenched sort of a corrupt system, and you have to be able to deal with it. And it's quite painful. We've had to let orders go simply because we didn't want to deal with that kind of corruption, or we didn't want to be part of it. But so the point I'm making here is that there is a lot more marketing than just the sales, and it's all that starts happening when you have a company that's actually building. I mean, the Quasar is much more like one of the innovative companies in the West than like any of the shops in India. Next. Now, the question that was always asked to us was that, I mean, all our competitors for every single product that we have, there are no Indian competitors. We are competing only with foreign MNCs. And everyone said that how will you ever compete with foreign MNCs? They have this, they have that, and all that stuff. People will not buy from you. They won't even believe, and so on. Right? That you have the stuff. I haven't had that problem so far, to tell you the truth. I mean, once I know that the thing is working, once I know that, I just go and I can get the atoms out, and that we are getting the atoms out, convincing other people that, look, you just come, you take a look, we'll just do it, we'll show you the thing, we'll show you the atoms, and so on. Is not, and once they see the atoms, now of course they'll ask questions like, okay, I agree that you're getting atoms right now, but how do I know that I'll continue getting atoms 5 years from now? So my answer was, well, you don't know. You don't know. I mean, I don't know because I am, it's only 5 years down the line. When we have a problem, we'll be able to fix it. All I can tell you is that we are making it right now. And, we can make one in a week, starting with the components. And therefore, if you have a problem, we'll fix it. Yeah, we'll fix it in less than a week. Yeah, we'll fix it hopefully in a day and do it. And so finally, the second thing, of course, that goes very strongly in our favor and that has helped us compete very effectively is that once people do become convinced that the whole thing is being done here, we have complete control of the technology. They know that we can maintain the system far, far better than any of the foreign companies. Because the foreign companies are all operating through local vendors, and those guys are mostly marketing types and sales types. And when they're talking to us, we are giving them insights. We're giving them insights into the science and into the whole technology, into how the whole thing is used. They're talking to us about customization. They're actually talking to us about their scientific issues. And we are giving them solutions which are going well beyond anything they themselves can even think out. So all of that is really good value for money. And therefore, we are not having too much trouble. Tell you the truth, handling competition. Next. All right, now the biggest thing, I mean, in the way in which we are doing it, ours is not a finance-driven company. It's not that we have a huge amount of, that we walk in with a huge amount of money that we've gotten from some other source. I mean, it's a bit like all these big, you know, the all these people who've made money in real estate or something, and have gone out and started engineering colleges, etc. And all these engineering colleges are, of course, running like ordinary businesses. They're running like shops. You have so many students coming in. There's a certain throughput. And but what we really, you see, for us, if we suppose we want to build something new, suppose we've already made say a scanning something like, and now we want to expand, and we want to build, let's say, an electron microscope. Now, you can't just go out and go into one of the IITs and you say, all right, you say that, we've come here recruiting for people who who can build electron microscope. You do that, you'll not find a single person. No Indian. In fact, let me be absolutely categorical. Nobody who's brown, nobody who's Indian anywhere in the world. In the US, we have never heard of an Indian who knows how to build scanning, say, electron microscopes. They do not exist. Now, if you have that kind of a situation, how do you move? All right. How do you go about actually figuring out how to make these microscopes? And now the problem is in fact much deeper. And the only way I can explain it to you, I've put down some of these things here, because these are just points, reminders to myself of what is to be explained. I've actually used up more than, I'm now on the 46th minute. I'll just do 4 more minutes and then open it out to questions. All right, I'll just explain the concept of, you see, if you have to be a musician, you have to either sing or play a musical instrument. If you do neither of those, you cannot be a musician. There is no way that you can go to class and take notes and so on and mug up those notes and reproduce them in exams and become a musician. It just will not happen. Cannot be done. It's a fundamentally different activity. The same is true of engineering. Unless you build things and you make them work and you do all of that, all right, there is absolutely no way that you're going to become an engineer. Now, in every single one of our institutions, people do not build. All right, let me be categorical. There are very, very few courses in the IITs where I've taught. There is one optional course in the last semester, and it's only an optional course in which is a project course. So if people have never built anything, they cannot be expected to build. All right, they're exactly like people who've never played or sang, or who've never sung anything. And if you're looking for musicians, you're not going to find them. So this is, and the second thing, of course, that happens in all our institutes is that we train people and we train them to run to the US and to the white man. We've had this long history of the white man coming and enslaving us up until, and up to 47, the enslavement was very direct. And after 47, the enslavement is very much there. There are 4 million Indians right now settled in the US, the so-called Pravasi Bharati or whatever they are. And all of them have run after independence. They didn't think that they could actually build, instead of being in India and building an AtmanirbharBharat and all that stuff, all of them chose to run. And they're all, even today, from the IITs, the moment people pass out, they're all running. And from other places also, they're trying to do it. And you say, it's like, still like people just being shipped out, and they don't know what they'll be going to. They're just going to that place, and whatever the white man asks them to do, they'll do. So the mentality is still, exactly the servile mentality. And therefore, all the learning that is being done in these places is learning that will be useful to the white man. Now, of course, the MNCs have come here, and the type of trivial work that they ask people to do is what, our institutes train them for. But if we have to build the types of things that we're building right now, it'll have to be a totally different thing. And we are having to take the full burden of that education in the company and pay for it. So anyway, these are a few observations that go with this whole thing. And I think next, and I come to the end of at least a few observations, and I'll now just take some questions quickly for another 10 or 15 minutes, if there are questions.
Yeah, thank you, sir, for nicely explaining how you started the company and then how you reached to this various instrumentation which you developed, and you also have this some of the instruments in the abroad, like you told the Singapore ones. So that's nice. And then participant, we request you to ask any questions related to this talk, because Professor Sahdev built this company after working several years as a professor at IIT Kanpur, and then he is starting this company. And this is also very good step or first step towards the AtmanirbharBharat to start this kind of ventures. So this kind of instrumentation are really required, not for everyone or for the particular group, but they are very important steps towards making this AtmanirbharBharat. So if you have questions, you please write in the chat box so we can take those Professor Sahdev. So I have the question: what you do for forecasting and posting demands for your instrumentation?
Sorry, can I see? Is it possible to see the person who's
No.
asking the
I am
question?
asking the question because right now we don't have any questions. So I have this question: what you do? What kind of strategy you follow for this forecasting and posting the demands for your company or instruments? What is your strategy?
Oh, right now um, uh, we don't particularly have to forecast the demand. We look at well, in the case of actually, since we weren't when we had started building this entire thing, we started building the entire the STM, etc. The problem wasn't so much we weren't thinking too much about the marketing and worrying about the demand. Our basic concern was, will we be able to build it at all or not? Because when I started out, I couldn't get anyone to even say that, yeah, all right, this is something which is possible and let's just try doing it. I mean, it was very difficult to even find. I found finally one of my friends and colleagues said, all right, let's try it out. So at that time, we weren't trying to forecast it, but now what we are seeing, there are two sides to what we're doing, and one is that we've in the case of the STM, we've had to create the demand. It wasn't already there. And in the case of the physical quantities measurement system, we also had to create the demand. In the case of the chemical vapor deposition system, the demand was already there. And now we are able to, and had been created by other people. So I guess that what we, it's, you see, right now there is a demand for COVID related things, all right, and it's not particularly difficult to forecast. But then the problem is that you have to have something to tackle the COVID crisis, and your company has to be involved in doing that. It's not that you suddenly a demand arises in some particular sector, and it is not quite related to whatever you're doing. So lots of people said, well, why don't you switch directions? I mean, we could in principle have tried to switch directions and started and try to make ventilators, for instance. But to make ventilators of that particular quality at a very low cost, is a 2 to 3 year exercise. And if we just try changing course, I mean, in 3 years, it's quite possible that the whole demand will go off. So one thing is that one can, if you see some particular direction in which there is demand, and it's going to be a persistent demand. Now, there is a persistent demand, if you like, for scientific instruments, but scientific instruments encompass something like, even if we take only major instruments, it encompasses something like 200 instruments, yeah? 300 instruments in physics and engineering alone, and it include biology and research in molecular biology, etc. It could turn out to be that many, and each of these instruments takes a huge amount of time to actually build. So even if one can see the demand, all right, it has to also be matched with capabilities. Right now, what is limiting us is not so much the demand as the availability of skilled manpower. Almost all the thinking and the innovation that we are trying to do is in how we can build up skilled manpower at a much faster rate. I mean, there are people now. I mean, obviously, from what we have built, you're able to see that that we must have people who are very good. Now the question is, how do you get these very good people to produce more very good people? And that, I think, is I mean, once we have that, and then it becomes, then we can respond to the demand at a much faster pace in say instrumentation and eventually in other things. So our route is somewhat different. You see, many companies are finance driven. You look at the Tatas, for instance. The Tatas, when they wanted to do Jaguar or Land Rover or something of that sort. They did not have people in-house who could produce cars of the same quality as Jaguar. After, I mean, the Tatas are a pretty formidable company. I mean, you go to Tata Nagar, they're running the whole place. You know, but in spite of all of that, they just didn't have that kind of skilled person power. What they had to do was to go out. Their whole approach was a financial approach. They went out and they just bought Jaguar. And with the buying of Jaguar, they bought all the people inside Jaguar who knew how to build the car. But they have not yet been able to transfer the technology to India at all. I mean, there aren't Indians who can build Jaguar. All the people who can build Jaguar are right now still just Englishmen and the white people and the Germans and so on. So this whole question of the indigenization of technologies, when do you have Indians who can do it and are doing it inside India? That is really the crux of the whole thing. And I do not see any way around, any way of doing all of this other than what we are doing. It's a slow process of somehow changing the educational system and focusing it on actually building things one after another. And having people now, all the people, Quasar is, I mean, the company built is a completely ideologically driven company. It's not either a finance driven company or anything about it. It's driven purely by ideology, believe it or not. And the people who have come in because they believe in this particular. I mean, a person turning down Princeton, Harvard, and Berkeley has to be, when he is very much capable of just getting into their top positions, has to be doing it for ideological reasons. I mean, he came back and he and this whole the way people describe. And by the way, because of this very reason, we do not recruit in any field other than physics. The only people who will actually do these kinds of things are physicists. And the whole company has been built by physicists. There aren't engineers in it. And if we want to do anything, you hire a physicist and tell him to learn mechanical engineering. You hire a physicist and tell him to learn chemistry. Tell him to learn biology, him or her, and it will happen. That's the only way we've been able to make it happen. We have never been able to hire a chemist to do chemistry or a mechanical engineer to do mechanical engineering. IIT Kanpur has turned out 3 brilliant people in electrical engineering. And over the last 20 years that I know of, 2 of them are physics and 1 of them is mechanical. There is nobody from electrical who ever reached that level or came to even 50% of that level, ever, in the last 20, 25 years. And I don't know about the previous 25 years because I wasn't there. But I suspect that it has never happened in all 50 years or 60 years of this is actually the state of affairs right now. But we have found a way around. We've just gotten physicists who are completely convinced and will take all these chances and will put in the 12, 14 hours a day, will think it out and will figure it out, and who have that particular passion. It has to be passion driven in India right now. It cannot be anything else, as far as I can make out. So maybe others have other views, and they can take.
Participant, we are running short of time, so we cannot take all the questions, but still I can take this one question.
Are there any questions at all? Maybe this talk is
I'm reading.
Finished off all questions. Yeah. People don't know what to make of a talk of this sort.
Yeah, I am just taking one more question.
Maybe Sandeep Patil can ask some questions since he's a panelist. Let him ask something.
Sandeep, do you have any question? Dr. Sandeep.
Yeah. Sir, I can ask anytime. Don't worry. I'll call you directly. So I'll let the audience call them. I mean, like they ask the question.
Okay, right. Okay, that's a valid point. We can talk separately.
Yeah.
I mean.
Okay, sir. So this one question, this last question, I can read this one. Sir,
okay.
Atomic level insertion is possible using tunneling, like we talk about the quantum tunneling, or this we use the example as an electron. The question is atomic level insertion is also possible or not?
Atomic level what?
atomic level. So atom can tunnel or not? So the question is, can atom tunnel?
Oh, the whole atom tunnel from one point to another.
Yeah, our participant is different. So you please, yeah, explain in brief, please.
In this case, it is electron tunneling. I mean, these are all electrons which are tunneling. But in principle, of course, you can have the all of alpha decay, for instance, helium nuclei which are tunneling out of nuclei. That's how those nuclei actually undergo alpha decay. So there are tunneling phenomena of bigger objects, but the probabilities for that type of tunneling is smaller and smaller, and it's in fact become so small that you almost never see them. So there is tunneling is a reasonably well-known phenomenon in nuclear physics, and also the tunneling of electrons is a well-known phenomenon. What we are using in this entire thing are the tunneling of electrons. But I mean, the questions that people can ask need not be scientific. I mean, this whole thing, they can be asking questions about this whole thing, about the business aspect and the entrepreneurship aspect of what I've said. I thought that I would have at least managed to provoke them to ask certain questions through my last slide, but even that doesn't seem to have done very much.
Yes, sir, we could have asked more questions. We are running short of time. So, yeah, myself, I have many questions. Yeah, I want to ask, but maybe I will ask later. So,
Right.
thank you, sir.
Okay. Sure.
Yeah. Thank you, sir, very much for this nice presentation. And I hope this participant will enjoy and they will get benefited from this presentation, and they will try to start their own companies, and they will really get motivation.
Well,
Like
they'll hopefully start their own building teams around wherever those activities. I mean, the team comes first and the business comes later.
yeah, maybe some of them, they can contact you, can get motivation and how to start, so you can help them.
Yeah, certainly.
Yeah. Thank you, sir. Thank you very much, sir, for taking this session. Thank you. We are really thankful for you for taking this session. That's will really get benefited. Thank you.
Thank you, sir.